All right, so let's go ahead and jump into 5.3 now. 5.3 is conditional probability and independence, okay? So stuff we've done before, we just haven't did some of the net nomenclature and stuff like that. So let's go back to our male and female pierced ears. Okay, let's go back to this example. And 1971, 84, 4, 103, 75, 178, 88, 90. So here we go. Okay, so a conditional probability is a probability given that something happens. Okay, given that something happens. Okay, so here we had P of A, and we called that the probability of being a male, right? And then we had probability of B, which was having pierced ears, right? Okay, so a conditional probability would be like this. So if I say PA, given that B had happened, okay? So this is what? Given that B, given that I have pierced ears, given that I have pierced ears, what is the probability that I'm a male? Okay, so pierced ears would be here, right? Pierced ears would be here. So out of the 103, there's 19 that were male. Okay, so this is an example of a conditional probability, right? So this reads as probability of A given that B happened. Okay, all right. So if we go to page, where is this? 331, there's a green box there. Go ahead and read that for me where it says conditional probability. The probability that one event happens, given that another event is known to have happened, is called a conditional probability. The conditional probability that event B happens, given that A is happening, is noted by that. So let's go ahead and do this. Let's go ahead and see what happens if I flip this around. If I flip this around, what happens? The probability of B A. Okay, so what is the probability given that I am a male and I have pierced ears, right? So given that I'm a male, right? So it would be this column here. I have 90, right? Out of the 90, I have pierced ears. That'll be 19. So you can see that really P of A given B and B given A really have no relationship to each other, okay? Because they're totally different things that they're asking for here, okay? So just go ahead and realize that. And then let's go flip the page, go to page 332, and we will welcome back our Titanic disaster example. So in the Titanic disaster, we had, okay, you survived, you are dead, and we have first class, second class, third class, right? So we have 197, 122, 94, 167, 151, 476. Add them up, we get 422, 765, 7, 8, 11, 87. So here we go. This is our table. So suppose we randomly select one of the adult passengers from the Titanic. Define events F, first class passenger, S, survive, and T as being third class passenger. Find probability T given S. So probability of T being a third class passenger and you survived, given you survived. So given you survived, up here, right? You're up here, given you survived, What is the probability that I'm a third class passenger, right? So it's going to be 151 over 422. Okay. B, given that the chosen person is not a first class passenger, what is the probability that she or he survive? Okay. So given that you are okay, so let's go ahead and do the notation here first. Given that you are not a first class passenger, is that what I said? Not a first class passenger. So first class will be the complement of that, right? The opposite of being a first class passenger. Given that you are not a first class passenger, what is the probability that he or she survived? So you survive, which will be an S. Okay. So if you're not a first class passenger, okay, how many first class passengers do we have? We had this many first class passengers, right? If I add these together, I get 319. So I'm going to be 1187 minus 319, right? What is the probability that I survive? So given that I'm not here, I survive would be this 2 right here, right? 94 plus 151. 94 plus 151. And that would be your answer. Everybody see that? Okay. Right. Good there. So go to page 333. On page 333, there is a green box there. It says calculating conditional probabilities. To find the probability, okay, so now here's an interesting thing. So PA given B is the same as PB, PA, and B. Okay, so this is a general equation. Okay, this is a general equation, something you need to know. All right. Okay, so with that, we're going to skip the next one over there, and let's go to conditional probability and independence. Hang on a second. Okay, conditional probability and independence. Okay, independence is often misunderstood or confused by you guys between independence and mutually exclusive. Okay, independent, you can think of it as this way. Independent would be the probability of me scoring 100% on an exam is independent with whether or not Claire is wearing a red shoe. Okay, they have totally no correlation, nothing together, right? Okay, whereas if you remember, mutually exclusive was what? Mutually exclusive would be the probability of you rolling one dice, and rolling a 5 and a 7 together, or 5 and a 4 together, right? It's impossible to happen. You can't, it doesn't happen, right? You cannot do that. Okay, that's what mutually exclusive is, okay? All right. So again, the difference between mutually exclusive and independent are totally different. Mutually exclusive, if you remember correctly, is this was what? This is going to be P, I'm sorry. So P A union B is equal to PA plus PB minus PA intersect B. We did this, right? But earlier when we did mutually exclusive, we said that if they're mutually exclusive, since A and B cannot happen together, this guy goes to 0. And basically all you have left is this. That's a mutually exclusive one, okay? Now the mutually exclusive in the independent events if you go to page 335, there's a green box there. And let's have Braden read the green box for us.
Which one?
The green box on page 335.
Okay. A and B are independent events if knowing whether or not one event has occurred does not change the probability that the other event will happen. In other words, events A and B are independent if P of A, B equals P of A, B to the C equals P to the A. Alternatively, events A and B are independent if P of BA equals P of BAC equals PB.
Okay, thank you, Braden. So basically, let's go ahead and read this again, okay? Basically, what it's saying is that the probability of A happening, given that B happened, is the same if the probability of A happening and B did not happen, right? Because this is the complement. So this is the probability of B did not happen. So the probability of A happening, whether or not B happened or it didn't happen, are the same. And they're the same P of A. Okay, again, the probability of me acing the test, given that Claire is wearing a red shoe, is the same of the probability of me acing the test, given that Claire did not wear a red shoe. They're the same probability. This would be called independence. Okay, does that make sense? Does that make sense? So the mathematical terms that we're using and the equations that we're using are totally different between independence and mutually exclusive, okay? All right, so always try to remember those two together. When you talk about mutually exclusive, in the future when we talk about those, think about independence. Do I still remember the difference there, okay? And when we're talking about independence, same thing. Then think of mutually exclusive. Oh, I remember we talked about those two things together and they are totally different, and you should be able to come up with an example for both of them, okay? All right, let's go ahead and flip the page. Let's go to the general multiplication rule. The general multiplication rule is nothing more than the rule that we already know. We already knew that this guy was equal to BPAB, right? I'm just going to multiply this guy over. And this is the multiplication rule. Okay? That's all it is. It's the same thing. All right? So let's go ahead and do the example there. It says teens and social media. Okay, teens and social media. Alia, go ahead and read the question for us.
The Pew Internet and American Life Project reported that 79% of teenagers.
Oh, hey, whose dog is this?
I'm sorry, it's my uncle's dog.
All right, let's have somebody else read this. Kayla, read this for me.
The Pew Internet and American Life Project reported that 79% of teenagers from ages 13 to 17 use social media, and that 39% of teens who use social media feel pressure to post content that will be popular and get lots of comments or likes. Find the probability that a randomly selected teen uses social media and feels pressure to post content that will be popular and get lots of comments or likes.
Okay. So we're going to say uses social media to be this. So uses social media, right? And then we'll have piece of B, which would be what? B would be feels pressure to get likes and comments, feels pressure. Okay. So this will be it, right? So we're going to use the general multiplication rule here, right? General multiplication rule, we're going to say P, we want to find uses social media and feels pressure, right? So this would be the same as what? This would be the same as times that, right? So P sub B is Field's pressure. What is the Field's pressure? Field's pressure was 39%. So this is 39%, right? And this guy here is what? Given that this would be 79%, right? So you just multiply those two together and you're gonna get 0.038. Okay, pretty simple, all right? So again, let's go ahead and take a quick now. Let's take a 5-minute break and we'll come back and finish up 5.3-2. Okay, we just did 5.3-1 and we will finish up 5.3.